Okay, in this video, I'm going to show you how to take apart one of these cans in an Atwater Kent Model 70 L2 chassis capacitor can. The capacitor cans have to be heated up so that the solder can be melted away, and I'm going to show you how to do that in this video. We will actually melt one of the cans using a torch, melt the solder and clean out the can. First, I'll show you one video where I actually have already taken the back off the can and how I stuffed it and reinstalled it into the chassis. Then I will show you on the second capacitor, the second part of the video, a can that hasn't been done, and we will take it with the torch outside, and you'll get to see the cool fire and flames and smoke as we heat it up and make it ready for using in the chassis. And so I hope you enjoy this video, and please consider giving it a like and a thumbs up, and subscribe to my channel. I'm going to be working on this, restoring this Atwater Kent and this chassis, and put it back in its case. And this one has a lot of issues. It has a burnt out transformer, a blown up speaker, a lot of cool things that we're going to have to repair. So subscribe to the channel, hit the bell, and you'll be notified when there are other videos about this chassis in this series. Thanks for watching. Enjoy the video. Okay, this is the power line. This one, I'm calling this one. So this one goes to through there. 2 goes to the far left. 3 goes to the second left from the left. 4 goes to the left of the transformer and down to the fuse. Okay, so I'm going to take them off, and yeah, I'm going to take them off and redo this cap. And I need to mark, I'll need to remember which side is the left. Okay, I got this can out and cleaned it up. I had to use a torch to get the bottom plate off, and that goes here with the fuse connector on those 2 screws. So what I did is I put 2 XY caps in here. I used the leads as a bus line to tie them all together. These are all grounded to the can here. And so I ran them out. I ran one of them, I wrapped it all the way around and soldered it to the can. So we're going to have a good ground, and that'll solder to a wire that's going to go on this screw with a lug, so that it'll be a really good ground, not just the metal contact here, but it'll be good ground. And ran them through and soldered them, cleaned up the can, which is really nice, because after I torched it, it was, well, you see it's even better. It looks better than the original ones that are in there. After I torched it, it was all pretty well black, right? Had to melt all the solder around the outer lid to get the lid off and get the old capacitor out. And here's the old capacitor that I got out of there. Actually, there's 4 capacitors in here. And of course, they didn't have across the line Y2 rated capacitors. These are X2, Y2. So these go right across the AC line coming in. Well, actually, there's a fuse in line, but still, they're across the AC line. If the capacitor is shorted, it would put, it would, either one of them shorted, it could put AC right on the chassis, and that's a shock hazard. But these X2, Y2 caps are designed, well, the one they're designed to handle like a couple thousand volts, but 2, they are designed to open and not short. So if they open, they just disconnect and they don't do any harm. And then these 2 are just 2 capacitors for the interior circuit, and they just go to ground, so it doesn't matter that they're in here. It doesn't even matter if they short the ground because they're just regular capacitors. However, they could put B plus on the ground, but still we're isolated to a transformer, so not a biggie. But this side is critical because this is the AC line, and we don't want the AC line shorting to ground. And plenty of room to get the can back in there. I used longer capacitors, they're rated at 630 volts, 0.1 microfarad. These are 0.01, which is what the schematic called for. And yeah, they'll do the job. So I'm going to put that back in. On the next one, when I go to take one of these out and try to use the torch to clean it out, I'll try to make a video of that. I got to do it outside, so it's very difficult. I have no way really to, well, maybe I can get a tripod out there and try to record that so you can see the process. It's nasty, a lot of black smoke that stinks. Don't do this inside. I wouldn't even do it in a garage, unless the garage door is open and you got a fan blowing. I would do it outside because no telling how toxic this stuff is when it's burning, all that gunk they put in there. So, but they're cleaned out now. Anyway, I'm going to get that reinstalled, and then we'll go to the next one. Thanks for watching. Okay, I got it back together. I ran the ground wire out here, put it on a screw lug. I crimped the wire and soldered it, so it ain't coming off. And it's bolted on there. Next, this goes on. And then we put the nuts to hold the fuse holder on, and then connect the wires. So, nice good ground there. Soldered on both ends, heat shrunk. Not that it needed to be heat shrunk, but it is for stability. And so we're in good shape. Okay, getting ready to take this one out, and you see what it looks like. And so hopefully you can see this. I'm going to be working over here, but you get the idea. Get my torch going. Okay, and what we're going to do is just heat it up and get that solder to flow down to one side and bang it out, and that's what I've been doing here on this junk box. So we just heat it up. I'm sorry that I'm in the way of the camera. I'm outside, so you see it starts to melt, and then you get this crappy black smoke. It smells awful. But the solder runs down, it drips off, the black stuff comes out. Get it to run to one corner, it drips out better. You see it dripping. Okay, set this off and see if we can get anywhere with that. You lay this down. Okay, and you take a razor knife and try to come in through the side here and get that cover off. And there it is. And actually this one came out better than the last one. The whole capacitor come out. And there's the inside of the box. I think what made the difference on this one is I used my solder sucker, and you can use wick, and I soldered the holes here and here to get so that the leads were just hanging, and so they just pulled right out. No one fell inside there, but you see the leads just pulled right out of the holes. And this one went on this side. It has the two capacitors that go together, and there's the number. Oh, and it's a little hot. And this one went across Okay, so these two leads came out of there, and this one went all the way across and connected to the case here. So that was the ground side here, and those two were there. So they were in series. Well, they were like parallel to the ground, right? Not really parallel, but, and this one didn't have a ground. It just went right across those two. So the other lead, the other lead came underneath it. I'm going to keep that one. That one came out nice. It's pretty cool. It's hot. Okay, so that's how that goes. So I'm going to stop the video and go back inside. Okay, and here's this capacitor that we took out that came out in good shape. And it says 26, and part number 17646. According to the schematic, it's a 0.12 that just jumps across the can, which I was showing you outside. The other two go here, and they're both 0.1s, and then they have the lead that went right through underneath this one and connected to the can, and that's ground. So, but since this one came out in pretty good shape, not ruined, don't appear to be ruined, it's just a little bend up on the cardboard there. Let's see, it's warm. Let's see if it's a 0.12 after 80 years and a torch. I kind of doubt. So, but the torch would have only affected it while it was hot, most likely. So it should have settled back to something close to where it was. Well, maybe not. It might have shorted it or opened it or whatever, but let's find out. Okay, there you go. It's a 0.296. Not bad for a capacitor that's been, of course I'm on the nanofarad scale, so you got to move the decimal place 3 points to the left. Of course you see it is leaky, it's jumping all over. But 0.29. So 0.29 after 80 years and being heated up with a torch. And of course now it's, cooling down. It's pretty cool, actually. It's cooling down, and so it's dropping in capacity, which is actually amazing. It's getting closer to what it should be, which, it's twice what it should be. It's over twice what it should be. It's way out of tolerance, but it's getting closer, right? It should be 120. It's 269 and dropping. So it's actually taking a charge, but it's taking a charge extremely slow because it's leaky as anything, and of course it's old, and we just put it through a torture test. But, the foil in here is fine, and the paper's fine. The wax might have got hot, but it had nowhere to go, so it stayed pretty close. Now you see it's slowing down. It's still dropping, but it's slowing down some. So let's give it a second and see what it sort of settles at. It's leaking, that's why it's dropping down slow. It should have already long ago stopped dropping down. As it builds up a charge across it from the battery in the meter, eventually it should build up a charge equal to the supply voltage of the meter that's testing it. And at that point it should stop, or relatively stop. And that's how the meter works. It measures the time it takes to charge to calculate the microfarads. How much coulombs of charge can it handle and in what amount of time before it maxes out. And that is used in a formula in the chip in the meter to determine its microfarads. Basic math, right? Algebra. So it looks like it's slowing down pretty good now. So we'll say it's 240. It might be a little bit less. It's supposed to be 120. So it's about twice its rated value, or what the schematic calls for. It's about 100% out of tolerance. So there's 240. So not quite, might be 98%, but you see how slow it's changing now. And there it is. It's pretty well maxed out at 293. But it's leaky. So as it leaks, it has to charge it more, which throws the value down. Okay, here's what I'm replacing it with. We do not have, they don't make 1.2 anymore. So I can't get 120 nanofarads because they don't make them. So what I got here, and these are not soldered yet, so it's going to be a little bit off, but not much. I twisted a 0.1 with a 0.02 or the 0.022. So this should be 122, give or take. And that's what I'm putting in. So let's see how close it is. So we'll connect it up with my leads here. Take it off that one, put it on this one. Apologize for moving the camera around. And there. Do you see how fast it went up and stopped? Look at that. Let's do it again. I'm going to shut this off and turn it back on. It's on ohms. I'm going to go right to nanofarads right there. Look at that, 128.6. So that fast. That's what a good capacitor does. Now this is 128 because, plus or minus 20%. So this should be 122. Well, 122, 100 plus 20% would be 20. So 120 plus 20% would be up to 142. That's not counting the 0.22. So, figure 10%. 122 at 10% would be 12.2. So that would be 122, 12.2, 134.2, that's 10%. At 20%, it'd be even higher than that. It'd be about 160, 150. That's what it's good to, maybe 140 something. That's what it's good to. That's the tolerance of the schematic, right? 20%. Well, we're so close to, we're not even 10%. We're not even 5% out with these brand new ones. But the bigger issue is how fast it stopped. That's because they're not leaking. Has nothing to do with the microfarad value. It has to do with how leaky are the capacitors. This thing that's 80 years old, one, it's twice its rated value, so it's way out of tolerance. Cool as anything though. Way out of tolerance, and it's leaky. It leaks DC really bad. And of course, the torch might have made that even worse, right? Because that makes it take some of the wax and separation, but out between the plates. However, these are paper between the plates. It's paper that's the actual electrolytic, and the wax is just to hold it in place, and it adds a little bit of electrolytic value. So all we might have done is flowed some of the wax, but we didn't burn the paper. The paper's fine. So, they're just that leaky. I mean, if I just took one out and just tested it, it'd be that bad, right? 80 years old, doesn't matter if it's in a can and I have to heat it. But there you have it. So what we're putting in is way within tolerance, and it'll stay there because it's polypropylene. It's not paper and wax. It's a composite plastic that will stay in shape. I mean, and they're rated at 630 volts, so they'll never see 630 volts. There is no way they're going to fail anytime soon. Okay, so anyway, I'm going to clean this case up and get all this soot off. That's the way the last one looked, sort of. Maybe not quite that bad, but I'm going to try to get as much of this soot off as I can and get these capacitors. These are the other two that go together. These two here are actually only need, these two are these two that go to ground, and I'm probably going to do it the same way out to one side or the other of the can. I haven't decided which yet. And then put a clip, like I did here, run a wire out the can and a clip to the chassis to give it a good ground. But these two are the ground, and these two tied together are going to be the 0.12. So there's 2 0.1s and a 0.12. Anyway, thanks for watching.